The idea of an inverse function is as follows. Suppose I have some rule f mapping x to y. If I can find a rule going from y back to x, then we'll call that rule the inverse function of f, and we will actually denote it by this horrible notation, f with a superscript of -1. Before I can tell you when these rules will exist, I have to give you some further notation and terminology. So a surjective function. F is surjective if the range of f is the same as the, we also call these onto functions. Injective function. F is injective if f of x1 equaling f of x2 implies x1 is equal to x2 for all x1 and x2 in the domain of f. We call these also. If you recall, when I was telling you about functions, I gave you the vertical line test. Well, we have the corresponding horizontal line test. Suppose I have the graph of a function. And so let's just draw a curve in the plane relative to some coordinate system. And suppose that this is the graph of a function, meaning suppose that this curve satisfies the vertical line test. Then, if we can find a vertical line that intersects in more than one location, we say that this curve does not pass the horizontal line test. And so, if a curve here does not pass the horizontal line test, and is the graph of a function, then this is not a injective function. It is not one-to-one. If instead we have the graph of a function relative to some coordinate system, so it passes the vertical line test. If every horizontal line intersects this curve in at most one location, then we say that it passes the horizontal line test. If the graph of a function passes the horizontal line test, then this function is injective. It is one-to-one. A bijective function, sometimes also called a one-to-one, an onto function, or a one-to-one correspondence. So either a one-to-one and onto function or a one-to-one correspondence. F is bijective if F is injective and F is surjective. Cardinality. The cardinality, denoted by CAR, of a set A is the number of elements in the set A. Note that if F is bijective, then the cardinality of the domain of F is the same as the cardinality of the range of F. In kindergarten, you first were introduced to this concept. They would line up milk glasses of milk and cookies. And they would then note that for every cookie, there corresponds a glass of milk. And so they put them into one-to-one correspondence. There was this bijective map from glasses of milk to cookies. The identity function, as we defined before, maps x to x for all x. It is such that f of the composed with the identity function is f. The identity function composed with f is just f. And so it acts like a identity. Well, that's why it's an identity function. The inverse function. Let f be a rule mapping f into y, and let this be an injective function. Then g being a rule mapping y into x is called the inverse of f, as denoted by g equals that, well, we denote g by f with a superscript of -1. If f composed with g is the identity function and g composed with f is the identity function. Note that some books require that it not only be an injective function, but a bijective function, because it depends on how you want to define functions. If the co-range is always required to equal the domain of the function, which in many books they are. So please note the following, and this is very important, that f superscript 1, -1, is not the same as 1 over f. So even though this looks like a exponent, it's not an exponent. So if I have a parentheses and a -1, that does mean take the reciprocal. Except, not always, except if I have f to the -1, this means the inverse function of f. Then a parentheses around it with a -1, that means an inverse function of this inverse function. So here it doesn't mean reciprocal. Here it does mean reciprocal. Here it means inverse. So this is inverse function. This is the reciprocal. The multiplicative inverse. Here, this is the inverse of the inverse function. So there are two inverses, neither of which is a reciprocal. Okay, will it let me write? Oh, okay, that's just, it's doing weird things again. Okay. So the inverse function. Okay, the domain of the inverse function is the same as the range of your original function. The range of your inverse function is the same as the domain of your original function. So let's do some examples. On page 391, determine whether each function is one-to-one. I could just draw the graph of this and show, and then do the horizontal line test on this. But I'm going to do this analytically. So suppose that f of x1 is equal to f of x2. If I can show that this implies that x1 is equal to x2, then we'll have that this is a one-to-one function, that this is injective. So replacing x by x1, replacing x by x2, I have the following. And so let me just bring the x2 to the other side of my equation and the x1 to the other side of my equation. Factor, difference of squares. Factor, difference of squares. Factor, difference of squares. Let's bring this to the other side of my equation. Why isn't it difference of squares? Okay. That was an error on my part. So I can actually factor out this. Let me add another page here. So I get x1 minus x2, x1 plus x2 times x squared, x1 squared plus x2 squared minus 1. Okay, so this says that x1 minus x2 is 0, or x1 plus x2 is 0, or x1 squared plus x2 squared minus 1 is 0. Here this says x1 equals x2, but here this says x1 is equal to negative x2. Here this says that x1 squared equals 1 minus x2 squared. So that x1 is equal to plus or minus the square root of 1 minus x2 squared. Okay, well, but this has to imply that only x1 equals x2. And so this is a contradiction. Okay, so therefore, this does not imply, right? Because you could have x1 equal negative x2. Not imply. That x1 equals x2. So we have that this is not a one-to-one function. So therefore, f of x equaling x to the fourth minus x squared is not a one-to-one function. And that's your answer. Okay. Let's do the following. Each equation defines a one-to-one function f. Determine f inverse and verify that f composed with f inverse and f inverse composed with f are both the identity function. So first, let's determine the rule to give me f inverse. So let's replace f of x by y. Let's interchange x and y. Finding the inverse function, if you notice, I was just changing the each x by y in that. This is problem 7. So if I look here, I just interchange the rule of x and y here. So f here mapped x to y. Now this inverse maps y to x. So if I be able to figure out the rule, that will give me the inverse function. So let's replace y by x and x by y. Solve. So take the cube root of both sides of my equation. So y plus 2 is the cube root of x. Subtract 2 from both sides. So y equals the cube root of x minus 2. Therefore, the inverse function is just given by the following rule. Then I have to find the domain. Verify. So now let's do some verification. So I want to verify that f composed with f inverse is the identity. So let's verify that. So let's look at f composed with f inverse at x. So wherever I see an x in the formula for f, I'm going to replace x by the rule cube root of x minus 2. And so let's replace x by the cube root of x minus 2. And this is just cubed. So f of x was x plus 2 cubed. And I'm just replacing x here by the formula given by f inverse, the cube root of x minus 2. Well, the 2's cancel. So this is just equal to the cube root of x cubed. Well, the cube root of anything cubed is just the original. So this is just equal to x. And so I verified that f composed with f inverse is indeed the identity function. It always maps some value back to itself. So let's do the f inverse composed with f. I want to show that f inverse composed with f is the identity. Wherever I see an x in the formula for f inverse, I'm going to replace x by the formula given by f, x plus 2 quantity cubed. So wherever I see an x in this formula for x cubed, Oops, that's a minus 2. I'm going to replace x by x plus 2 cubed. Well, the cube root of x plus 2 cubed is just x plus 2. The 2's cancel. And so this is equal to, let's move this down. And so this is equal to x. And that's what I wanted to show. Okay, so let's do problem 57. Or maybe I should just write QED so you know I'm done. So I'm done. The function f defined by the given equation is 1-to-1 on the given domain. Find f inverse of x. Okay. Actually, let's see. Do I have, let's actually modify this. I'm going to have it equal minus. So this is, so 57-ish. So I'm going to change this from a plus radical 4 minus x squared to a minus radical 4 minus x squared. Okay, so y, well, actually, let's do this instead. Let's keep it as the plus here, but let's make it minus on this side. Let's do that. That'll be more interesting. Okay, so let's do that. Okay, so I'll let f of x equal radical 4 minus x squared, but the domain will be -2, the closed interval from -2 to 0. So this says the domain of f is -2 to 0. But that means that the range of the inverse function is the same as the domain, which is -2 to 0. And that's going to be important. Okay, so let's replace f of x by y. Square both sides of my equation. Solve for interchange. Oops. Wait. Interchange x and y. Square both sides of my equation. And so I get x squared equals 4 minus y squared. Solve for y, so add y squared to both sides of my equation. Subtract x squared from both sides of my equation. And so, oops, let's get another page. So I get that y is equal to plus or minus the square root of 4 minus x squared. Let's try to determine what the sign is for this. And so the range of my inverse function is negative 2 to 0. They're negative numbers. And so these y values here had to be negative. And so y must equal minus rad 4 minus x squared. So F inverse has to equal minus rad 4 minus x squared. And that's your answer. Find F inverse, and that's it. So I found F inverse. Okay, but notice that it was very important that I used the fact that they gave me the domain of my original function, which gave me, actually, let's make this a little bit more room, which gave me the range of my inverse function assigned to use on this. Okay, let me do the next problem. I'll move this all the way up because now I have room. Find the domain and range of f. Find the range by finding the domain of f inverse. Oh, okay, so we had like tricks before to find ranges, but now we'll find the range more easily by looking at the domain of the inverse function. So first, let's find the domain of the original function. Found by setting the denominator to 0 and solving for x. So the domain of my original function is just a set of all x's not equal to negative 3. It is the union of these two open intervals. So now let's determine the rule that gives me f inverse and then find the domain of that. And so f of x is equal to x minus 2 over x plus 3. Let's write f of x as y. Interchange x and y. Solve for y. So first, let me multiply both sides of my equation by y plus 3. And so I get x, y plus 3x equals y minus 2. Let me subtract, let's do it this way. Let me add 2 to both sides of my equation, subtract x, y from both sides of my equation. And so let me factor a y from the right-hand side, and write it on left-hand side. Divide both sides of my equation by 1 minus x. And so I get that the inverse function, has the following rule. It's just equal to 3x plus 1 over 1 minus x. So now let's find the range of f. Using the fact that it is the domain of my inverse function. And so the domain of f inverse is just found by setting the denominator to 0. And so I get here that x is equal to 1. So the domain of f inverse is a set of all x's not equal to 1. And let me actually write it this way. I'm going to write it both ways. And so the domain of f inverse is a set of all x's not equal to 1. Therefore, the range of my original function is just a set of, we don't call them, in this case, x's because it's a range. So you would actually say the set of all y's not equal to 1. That's why I wanted to write it this way. And so the range of f, again, is just minus infinity to 1 union 1 to infinity. And that is your range and your domain